Hello viewers, in this video I will be discussing a very interesting problem, finding the vertex, focus, axis and directrix of a general parabola. What do I mean by general parabola is that in a general parabola, it's something of this kind. It cannot be simplified in the form of y square is equal to 4ax or y square is equal to minus 4ax or x square is equal to 4ay or x square is equal to minus 4ay, or maybe y minus some constant, let's say y minus k square is equal to 4ax minus h. Not also in this kind of form it cannot be done. Y minus k square is equal to minus 4ax minus h. These are very simpler forms. These kind of parabolas, like this one, y square is equal to 4ax, this is this kind of a parabola, right? Horizontal, and it has the vertex at 0 0, but it might be shifted. The second one, this is the first one, the second one might be shifted somewhere with the vertex at hk. And so these are like horizontal parabolas. These are like horizontal parabolas, but in in the opposite sense. And the third case could be like the vertical parabola, and they could be displaced somewhere also in when you put x minus h square is equal to 4a y minus k. And the last one could be a downward kind of a parabola, which could be displaced somewhere when you do the transformation hk. But in all of these equations, you see there is no xy term, 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 and here you have an xy term. And first of all, you might be asking, how are you sure that this is a parabola, this equation is a parabola? I will deal with it also slightly in this video. Maybe I'll do a separate video on identifying the conics without memorizing any formulas, of course. So yeah, this is a parabola, but this is not a horizontal or vertical kind of a parabola. It is some, it might be like this, or maybe like this, tilted. This is a tilted, twisted kind of a parabola, which is very difficult to deal with. And normally how people deal with is that they rotate the coordinate axis and translate the origin and do two kind of a transformation, and then they it's a long story, and then they figure out in the new coordinate system that the parabola is either vertical or horizontal, and then they backtrace the focus, axis, vertex and directrix of the parabola. So that's very cumbersome. That's very, I don't like that method. So that's why I was thinking maybe using some kind of geometrical properties of parabola, we can figure out the vertex, focus, axis and directrix. So I did figure out a way to deal with parabolas. I am currently figuring out another way to deal with ellipses and hyperbolas, but the parabola case has been closed. Let's see how. So first of all, I would like to also show you this interesting thing. Like, I begin to think, how do you figure out, like, suppose if you are traveling on a parabolic path and that path is very big and you are a point and you're traveling, how would you know that you have reached the vertex? And if the path was very short, you would never be able to, sure, I think, unless and until you have that mathematical ability. So it's not a very easy question, right? Once we have this whole section of a parabola, then we begin to feel where the vertex is. It's not there. It could be somewhere here, yeah, it's somewhere around here. But mathematically, I have to figure out that vertex and also the axis exactly. So there is a construction, there is a construction algorithm which can be used here. So yes, the idea is perpendicular tangents. Perpendicular tangents. So perpendicular tangents are very easy to draw physically also. You just have to take a point on somewhere on the parabola and draw a tangent. And drawing a tangent is very simple. It's like you have a line and you and suppose these are physical things. You have a line and this is a physical thing, and you are moving this thing unless and until it touches the parabola. And suppose that they are solids, and when the thing touches this thing, you get a tangent, and it's very easy to get a tangent physically, and also geometrically it's not that difficult. So, and then I have to get a perpendicular tangent. This is a normal, this is a normal, this is not the tangent, but I will shift this normal slightly, slightly, and then I will get a tangent. This is also not very difficult to see physically. So we can draw a pair of perpendicular tangents, and perpendicular tangents are very important in conic sections and coordinate geometry. Now I have begun to realize their importance. So you can also do it in a very fun way, like you have a pair of perpendicular lines and you take them close to the parabola and you rotate them and fix them, just fit them in the parabola, and you will get a pair of perpendicular tangents, physically speaking. And you will also get the point of contact, of course. So once you have a pair of perpendicular tangents, there's a very important interesting property of parabola, is that the locus of the points from where perpendicular tangents are drawn to parabola is not a directed circle, it's actually the directrix of the parabola. But I can't go on drawing a lot of tangents and figure out the directrix, that would be too long. I will do something else, but this point is on directrix. I will prove all these things later in this video, just stating the facts. And then what you do, you draw normals and you figure out their point of intersection. Okay. And then what you do is you draw the chord of contact. This is chord of contact. And then what you do is, from that external point from where, which is on the directrix, from where the perpendicular tangents were drawn, you draw a perpendicular to the chord of contact, and the foot of perpendicular is the focus. This point is the focus. Believe it or not, this point is the focus. And once you have had the focus, then you can have the axis. The axis will pass through the focus, but the axis is definitely not like this. The axis is somewhere like this, or maybe like this. How would you figure out the slope of the axis? You know the focus of the parabola, you know the parabola is there, and how would you figure out the slope of the axis? You can say that this is obvious, one can definitely see, but mathematically, to figure it out exactly how to figure it out, there's another property which is not very important, not stated in any of the textbooks, but I figured it out, that when you join these 2 points where the normals are intersecting and from where the perpendicular tangents were drawn, just join them, and this line, I will prove it to you later, that it will be parallel to the axis. So the axis should be parallel to this line. So now the green one is the axis which is passing through the focus, the parallel line to this special line here, and passing through the focus. This is the axis. And once you have the axis, then you have the vertex also. And since this point lie on the vertex, on the directrix, so the directrix is also perpendicular to this green line, the axis, and you have figured out everything. I will repeat this thing again after proving the properties which are involved here. So let's see the properties. To prove the properties which I am using here, I will use a standard parabola, y square is equal to 4ax, and the focus will definitely be a0, and the directrix with x will be x is equal to minus a. So this is not cheating which I am doing here. I am going to use coordinate geometry for some time to prove purely geometrical properties. Okay, So stick with me. Otherwise, if one tries to prove it using pure geometry, it would be a little bit more difficult, yeah, but it would be purer. But I thought, why not to get a little bit more simpler? So let's go into it. I can take a parametric point at squared to at on the parabola. I can differentiate the equation to get the slope of the tangent, and I can write a tangent. The equation of the tangent will have the slope and will be passing through this point. So that's why this kind of an equation. You can simplify this equation, and you have tangent. Now you want to draw, you know that you can expect from what I told you before that the perpendicular tangent will be passing through this point on the directrix. But there's one more very interesting thing which will happen here. You can see from the dy by dx that the slope of tangent is 1 by t, right? And what is this t? This t is a parameter which you can associate with any point on the parabola. For example, here at the vertex t is equal to 0, because you put at squared to at, you put t0, you get 0 0, which is the vertex of this parabola. At the ends of the latus rectum, the t is +1 on the upper part and the t is -1 on the upper part, on the lower part, sorry. And then on this whole upper part, the t is positive. From here, the t is 0, it goes to t is equal to 1 here, then t is equal to 2 will be somewhere here, then t is equal to 3, and then all the way to t tends to infinity. Then down here you see the t is decreasing at the end of the latus rectum. In the downward part, the t is -1, then here t will be -2 somewhere, here t will be -3, and then all the way to t minus infinity. T is a parameter, very useful parameter. So in terms of that parameter, the slope of the tangent is 1 by t. And if I need a perpendicular tangent, I need that tangent to have a slope minus t, because 1 by t into minus t will be -1, which is the condition for two lines to be perpendicular. So then you can write that the dy by dx of the perpendicular tangent is minus t. But using this form, I can say this is 1 by -1 by t, right? So that new t, where the slope of tangent is minus t, that t dash, I can say, is -1 by t. So this is t is equal to t, and then somewhere where t is -1 by t, the parameter is -1 by t, at that point I will have that kind of a tangent, if you know what I mean. Then there's another very interesting thing that so that the point which we are looking for is a -1 by t squared to a -1 by t. This kind of a point will be here. This kind of a point will be, you can get this kind of a point, the reciprocal point I can call it, by passing through the focus of the parabola and reaching the other end of the parabola. You see, we already have seen for the latus rectum. The latus rectum, it passes through the focus, and there the t is equal to +1. And when you go down on the other part and reach the other end of the chord, you get t is equal to -1. So I'm basically saying that if you have a focal chord, so if you have t is equal to 5 here, you will have t is equal to -1 by 5 here for y square is equal to 4ax kind of a parabola. This is a very important property. The proof is very simple. You can just check it. So you can figure out that this slope and this slope will be same. So this slope 2at minus 0 divided by at square minus a. So this turns out to be 2at a, so 2t by t square minus 1. Now about this slope? Okay, minus 2a by t minus 0 by a by t square minus a. Let's cancel out the a. Minus 2 by t, 1 minus t squared by t square. Yeah, they're same. So if t is equal to t here, then t is equal to minus 1 by t on the other end of the focal chord, and from there you can draw that perpendicular tangent. And the equation of that tangent would be, you can just take this equation and put minus 1 by t, put t is equal to minus 1 by t. Anyways, and then you can figure out this point of intersection, you can solve them. So you have these two equations, this one from here and this one from here. How do you solve it? So you can, yeah, you can just subtract them. So when you subtract them, you get this thing, and t square minus 1 by t square, solve it a little bit, factorize, cancel it out. What happens? Y is equal to a t minus 1 by t, fine. And then put this thing in one of the equations. Let's put it here maybe. So what do we get now? This is very interesting. For x you will get minus a, as we expected, because this x is equal to minus a is the equation of directrix, and this point is lying on the directrix because the x is minus a, right? Fine. Now the next thing is that we have to draw a perpendicular. You have to draw a perpendicular from this point to this line, and this will definitely meet here at the focus. This was how we figured out the focus. So I will prove it to you. There's not much to do. So the slope of the red line, you can see, so you can subtract at minus 1 by t by 0, and then minus a minus a, so minus 2a, and then you solve it a little bit and you get this slope. How about the slope of the gray line, which we did before also? Let's do it again. So 2at, and this time I'm using only these 2 points, this one and this one. So using these 2 points, 2at minus 0 divided by at square minus a, and just rephrase it a little bit, and yeah, you can see that these two slopes multiply to minus 1. So this is the perpendicular. This should be the foot of perpendicular, and there is only one perpendicular from an external point to a given line, so there's no confusion about that. So the focus is, this is how you figure out the focus. Okay, so the focus is the foot of perpendicular from a point, from an external point on the directrix to the chord of contact, right? Anyways, and then you draw the normals, and then you have the equation of the normal. How do you figure out the equation of the normal? This is the slope of the tangent, then the slope of the normal should be minus t because it's perpendicular to the tangent, and then you have this kind of a point. You can figure it out. You can write y minus 2at is equal to minus t times x minus at square, and you can solve it a little bit and you will get this thing. So this is the equation of the tangent, then equation of the normal, then the second normal, and you can figure out that point. The second normal can be written just by replacing t with minus 1 by t, and then you can simplify it a little bit, and then you can solve these 2 points. Okay, so how do you solve that? How do I solve it? So you see, what I have done here is what have I done here? Oh, I have just added these 2 equations, this equation here and this equation here. I have just added so that the xt and xt cancels out, and I get y. The coefficient of y is now 1 plus t square. The 2at and minus 2at cancels out, and this is at cube minus, you get at cube minus a by t. You take out common a by t and you get this thing, and you solve it a little bit, and you solve to get the y, and that y should be a t minus 1 by t. You can do it on your own if you wish. Then what you see, that this y coordinate is also a t minus 1 by t, and this point also has the same y coordinate as this point. So this is basically, this whole line is y is equal to a t minus 1 by t, right? So yeah, so this is y is equal to 0, the axis is y is equal to 0, and this line is y is equal to something. This is parallel to the axis. Okay, this line is parallel to the axis. Take a look at it again. So now I'm going to show the algorithm, the construction algorithm again after proving these things. So what you do is that you have a pair of perpendicular tangents to the parabola, and then you draw the normals, and then you figure out this point, you draw the chord of contact, then you have this point from where the tangents were drawn, and from this point you will draw a perpendicular to the chord of contact, and then you will have the focus. Okay, and then from this point, from the same point, you join the point of intersection of normals, and you'll get a line parallel to the axis. So that's why you can figure out the axis very easily, the green line. And once you figure out this point is very important. This point is on the directrix also, and the directrix is perpendicular to the axis. So that's why you will have this directrix like this, and obviously the vertex will be here. Okay, so this is the algorithm. Let's see how I will use this to find out the vertex, the axis, the focus, and the directrix of this twisted parabola. So what I will do is I will rephrase it as a quadratic in y. Okay, so I have a y square term, I have this term with as a variable coefficient of y, and this term I can treat this as a constant term, and I can solve this thing. I can solve this quadratic to get this expression, and something very interesting happens. You see, this is the discriminant here, b squared minus 4ac, and when you write this thing, you figure out that this discriminant could have been a quadratic, but it's not quadratic, this is linear, and that is the key. That is the key for parabola. When you have such kind of a discriminant which is linear, then you get a parabola. I'll do a separate video discussing about these things, but for now we have another task in hand. So this becomes 2x minus 1 and 15 and simplifies to this thing. So now I see that for y to be defined, 2x minus 1 should be greater than 0 because it's here inside the root, and 2x will be greater than half. So whatever this thing is, whatever the shape is, the shape would not be defined for inputs less than half. It will not give you any y. Okay, so figuring that thing out, I can show that this is x is equal to half. The shape cannot be behind this bar. It should be here in this section, not here, because at this point you will get, if you put any x, you won't get any y. Okay, so, and also if you put x is equal to half, you will get only one output for y, right? Because this thing will become 0, and then you will have, if you put x as half, so 7 plus half by 2, you get y is equal to 15 by 4. That point is somewhere here. Fine. This kind of thing you can also do with x. You can turn it into a quadratic of x and use the symmetry of x and y. So you solve it and you get a linear term once again. So this is very interesting. You will get a linear term from both the sides. Does it need to be proven? I don't know. Anyway, so you get a linear term in terms of y, and this y, now you see that this is defined only for y greater than 0, right? Because inside the square root you have root 15y, so that will be defined only if y is greater than 0. So you have similarly y greater than 0, y is equal to 0 is this line, so that figure should be in this section only. It can't be here, it can't be here, it should be in this section. Okay, so what now? If you put y is equal to 0, you get the point 80. So only one x output, 80. So these 2 points are definitely on the curve, and the curve is passing is in this section, and you begin to feel that this should be a parabola. But I will do a separate video about this very soon. Anyways, now you can imagine that if parabola is like this, something like this, these are the perpendicular tangents, right? This line, very simple equations. Y is equal to 0 and x is equal to half are the perpendicular tangents to the parabola. Okay, and so what do? We draw the chord of contact. And from this point, 1 by 2 comma 0, the perpendicular tangents have been drawn, and this point will lie on the directrix. This is the very important point. From here we will start to draw some lines. We will draw a perpendicular line and we will figure out the foot of perpendicular, and this will be the focus of the parabola. How to figure that out? So you just figure out this line, the slope of this line, 15 by 4 minus 0 and 1 by 2 minus 8, and that turns out to be minus half. And then you write down the equation of this line. So from the equation of this line, I can take a general point. So if I put x is equal to a, I get y 4 minus a by 2, and then I figure out this slope. Which slope? This slope, right? So 4 minus a by 2 minus 0, a minus half, and then I simplify that thing. And remember, the slope was minus half, so if they are perpendicular, this slope should be 2, and then I solve for a. Very simple. And then I put the values of a in this point here. Before, you see, this point was a 4 minus a by 2, and now I know that a is 2, and then I will put, whoa, a is equal to 2 here, and I'll get the focus. The focus is 2 comma 3. Not that difficult, much easier than the transformation of axis kind of algorithm. Anyways, so this is the focus, and now what do? We draw the normals. The normals are very easy. These tangents and these normals are parallel to x and y axis. This is very easy to solve. And where do the normals intersect? This point, it's very easy to see. This 8 and 15 by 4, right? And then what you do, this is the important point from where we will draw, we'll connect this line, and this will be parallel to the axis of the parabola. What is the slope of this thing? So 15 by 4 minus 0, 8 minus half here, and you solve it, you get f is equal to minus half. Very good numbers you are getting. Yes, so this is now the axis of the parabola, which will have the same slope, right? M is equal to half. This line, these two lines will be parallel, as we proved before. And then you figure out the axis of the parabola, put this point 2 3, and then use this slope. You can figure out the axis of the parabola, and then the directrix will be passing through this very important point here, and its slope would be minus 2, definitely, because these two lines are perpendicular. Then you can figure out the directrix also. Fine. What's next? Other things are just formalities. Now this point of intersection you can figure out by solving. This will be minus 2 by 5, 9 by 5. This what is this point? This is nothing. Actually, this is the foot of perpendicular from focus to directrix, but the midpoint of this point and the focus would be the vertex of the parabola, and that will turn out to be 4 by 5, 12 by 5. See, so that is it. The parabola is it. This is the focus, this is the directrix. The parabola is something like this. It will touch this, and this. So you can generate the parabola on Desmos or GeoGebra, whatever calculator. You will see this kind of a parabola for this equation. checked it. You can also check it on your own. This whole the drawing, deliberately I have not done it to the scale, because this is what students face when they are solving this kind of a problem. So I have deliberately not done it to the scale. That's why you don't see a very good parabola. But yeah, everything is proven, and I think this is a simpler way to deal with these kind of problems. Thank you.